We now move to session 1, for which the moderator is Vice Admiral I.C. Rao, PVSM, AVSM, Indian Navy retired. And the two speakers are Lieutenant Commander Solanki of the Indian Navy and Mr. Pankaj Misra of Wärtsilä. Let me introduce the moderator, that is Admiral Rao. He's a graduate of the National Defence Academy when it was, I think, the Joint Services Wing at Dehradun, as well as the Royal Naval Engineering College, Plymouth, United Kingdom. He was commissioned in the Indian Navy in 1956 and served for 37 years in the engineering branch until 1993. He has served in various sea appointments, including as the engineer officer of the old INS Cauvery, thereafter INS Trishul, and lastly INS Vikrant, which was at that time the flagship. Ashore, he has served as the staff officer at the DME Naval Headquarters and as an instructor at the IIT Pune. He was a chief project manager for manufacture of Allen's auxiliaries for the Leander project at the HAL Bengaluru from 1976 to 1978 and commanded Indian INS Shivaji, which is the alma mater of all naval engineers from 1978 to 1980. He was thereafter the general manager Naval Dockyard Visakhapatnam from 81 to 85 and the first director of defense machinery design establishment at Hyderabad from 1985 to 1988. Subsequently, he took over as the Admiral Superintendent of the Naval Dockyard Mumbai and served there from 1988 to 1990, before culminating his illustrious career as a Chief of Material at Naval Headquarters from 1990 to 1993. And for distinguished service of an exceptionally high order, he has been awarded the PVSM and the AVSM by the President of India. May I request Admiral Rao to commence session 1.
Thank you. Thank you, Admiral Nadkarni. We are at the start of a very interesting day, and we thank Commodore Chitnis for his welcome address and a brilliant exposition of the entire marine engineering history and the future by Mr. Ajay Chatterjee. And we have got two speakers in session 1. That is Lieutenant Commander Solanki and Mr. Pankaj Misra. Now, Lieutenant Commander Solanki, I think, has done a lot of research and he's brought out many new facets which were not known to many of us. And we look forward to his address because change has been very rapid. I remember serving in a ship where we could have the entire machinery systems working without electricity. In INS Cauvery, right from the capstan and the forecastle to even the steer, we did not even have steering motors. Even the steering was by steam engine. Everything was run by steam, but in my own generation, everything has changed. So to record this change, may I now request Commander Solanki to share his screen and start his presentation. Because I think we are short of time, I will not delay this proceedings any further. Lieutenant Solanki, please.
Hi, sir. Sir, can you see my screen, sir?
Yes, it's clear.
Yes.
Sir, request permission to start.
Please start, yeah.
Good morning, sir. The history of development of marine propulsion is filled with tales of great human endeavor and perseverance. I would primarily focus on the historical perspective leading up to the era of steam propulsion from oar to sail to steam. The scope of the presentation is flashed on the screen. First, I will briefly discuss about history of marine propulsion. The earliest historical evidence of the existence of boats has been found in Egypt, dating back to the 4th millennium BCE. Egypt's culture was completely riparian as it existed along the river Nile, and all requirements of the civilization were met by transport through the river. Because they were confined to the Nile and dependent on winds, recourse to rowing during lull periods was essential. Early Egyptian boats had a single square sail along with one row of oarsmen. The role of the ship defined the design criterion, which still stands to this day in classification of various ships. Fighting ships required speed and adequate space for substantial number of fighting men. In contrast, the requirement of trading vessels was to carry maximum quantity of goods along with minimum crew. As per Indian mythological records, evidence of boats was first mentioned in the Ramayana, where Kevat transported Lord Rama across the river Ganga. As per history, shipbuilding in India goes back to the 3rd millennium BC to the Harappan times, that is during the Indus Valley civilization. The Harappans built the first tidal dock of the world at the port town of Lothal in about 2500 BC. By about 200 BC, old ships were built in larger and larger sizes in the modern era. The wood used was mainly Malabar teak, which was superior in durability. When trade winds were discovered, multiple old galleys gave way to sail ships. Skill of navigation with the use of sails was being discovered in the early centuries, where sailing under following winds was only known to a few seafarers. To achieve better speed, more mast and more sails were required, which provided stability to the ship but also covered larger deck spaces. Two types of sail, the square and the lateen, were extensively used. Various combinations of sail were tried by seafarers over the centuries, but more often, the second mast always carried a square sail. The Portuguese are credited with introducing guns on board ships that were constructed in India. The shipbuilding style of Portuguese was greatly followed by the Marathas in 17th century. The Garup and the Gulliver were two prominent fighting vessels of the Maratha Navy. The Gulliver had two masts with a lateen sail and benches for oarsmen. The first keel of the Maratha Navy was laid near present-day Kalyan. During the 18th century, the Parsi community became pioneers in shipbuilding. They built various ships for the East India Company and mastered the art of shipbuilding. HMS Trincomalee, built by the Wadias in 1812 for the British Army, is still afloat at Hatpool, England, and is testimony to India's traditional shipbuilding prowess. The Wadias also developed sites for construction of ships at Surat, Daman, and Bombay. Shipbuilding had also developed in China by 1100 AD. Chinese ships were better in design as they provisioned for rudder along the keel at the stern of the ship, which provided better stability and control. In rigging, Chinese ships were far ahead of the Western ships, with sails made of narrow vessels, each tied to a sheet at each end so that the force of the wind could be taken in many lines rather than on the mast alone. By the 15th century, Chinese junks had developed into the largest, strongest, and the most seaworthy ships in the world. Not until about the 19th century did Western ships catch up in performance to these. Major developments from the 15th to the 19th century will be discussed in subsequent slides. The early 15th century saw the rise of full-rigged ships because trade was becoming larger in scale, more frequent in occurrence, and more distant in destination. To achieve greater speed, multiple masts with more canvas of sails were added, which made them capable of covering larger distances. To accommodate additional mast, the hull became elongated. During the 16th century, carracks, which were Mediterranean three-masted ships, were largely in use. As the year passed, the galleon, which never carried oars and were likely to be four-masted, became the most distinctive vessel. During the 17th century, vessels were commonly three-masted in Northern Europe. The Dutch, competitors of England, were able to build and operate merchant ships more cheaply with half of the crew of English ships. In the 17th century, the sailing ship in general service was predominantly the Dutch fluid, which made Holland a great maritime power. In the 18th century, England re-established its prowess over sea trade by extensive studies on material of sail and enhancement in design of the box rudder. The 19th century saw the rise of America's power in shipbuilding. Americans studied the existing weaknesses of British ships and constructed more advanced ships with several improvements over the existing rudder design and rigging techniques. American clippers were better in speed than their competitors and operated with minimum crew. These were long, graceful, three-masted ships with projecting bows and exceptionally large spread of sail. However, by the turn of 20th century, the last of the mast on passenger ships had been removed. Although the use of sails by commercial purposes were phased out by the beginning of the 20th century, leading navies of the world still operate sail ships to impart training to their men. The Indian Navy also operates two sail training ships, INS Tarangani and Sudarshani, for providing sail training experience to officer cadets. INS Tarangani, commissioned in 1997 and built by Goa Shipyard Limited, was the first Indian naval ship to circumnavigate the globe. Indian naval officers have also circumnavigated the globe on Indian naval sailing vessels Madai and Tarini. Moving on to the evolution of marine steam engines between the 17th to the 19th century. The main drawback of the sail ship was that as the ships grew larger to cater for more cargo, the sails along with handling equipment also grew bulkier. This became cumbersome and problems arose in reliability and maintainability of equipment, thus triggering research in other forms of propulsion. Along with the discovery of various properties of steam as main propulsion, the design of propeller was also being conceptualized by scholars. Among the first batch of designs, paddle wheels driven by steam engines made their way as propellers for the ships in the 18th century. Initially, two designs of paddle wheel, straight paddle and rotary paddle, were developed. Screw propellers, which were designed by Colonel John Stevens in 1804, faced multiple problems in their initial days. The history of the steam engine is linked with the invention of the steam pump. The steam pump was marinized and adapted for use on board vessels as the steam engine. The founder of the steam engine was Thomas Savery, who invented a steam pump that was extensively utilized in the mining industry and was also known as the friend of the miner. Savery's design was upgraded by Thomas Newcomen, whose engine had better efficiency. The engine was self-acting in nature and had an added feature in the form of a condenser that considerably improved its fuel efficiency. James Watt is credited for developing the steam condenser engine in 1765. This was an improved version of Newcomen's fire engine. Watt developed the pickle pot condenser, which was later replaced by the common jet condenser in 1800. This engine, which utilized vacuum underneath its piston, had better fuel efficiency than previous engine designs. On August 9, 1803, Robert Fulton, an American, made history by successfully completing river trials of a steamboat on the river Seine at Paris. The steamboat operated at 3 miles per hour. Fulton utilized James Watt patented steam engine and coupled it with a rotary paddle wheel for propulsion. In 1819, the Savannah, built by Savannah Steamship Corporation in New York, became the first ship to successfully cross the Atlantic Ocean. The ship was propelled by sails and paddle wheels powered by a steam engine. The engine powered the paddle wheel for a total duration of 85 hours. The first marine steam engine for cross-Atlantic liner ships was developed by I.K. Brunel in 1838. This engine was installed on board the Great Western, a cross-Atlantic liner of the Great Western Steamship Company. The engine was operated on a low boiler pressure of 5 psi and developed 450 nominal horsepower. The propulsion system of the ship consisted of a steam engine, sails, and paddle wheels. The Great Britain was the first iron steamer to cross the Atlantic and was built by I.K. Brunel for the Great Western Steamship Company. The ship was the largest of its time and was propelled by a steam engine connected to a screw propeller. An auxiliary sail was provided for additional power. Some of the design challenges that were associated with initial designs of steam engines are requirement of large engine room as the engine size was not compact, use of only heavy cast iron in engine construction due to insufficient knowledge of metallurgy, problems in connecting pistons and cranks as the technology of bearing materials had not developed, slow rotational speed due to low boiler pressures, high consumption of fuel, and lack of skilled operators. Sir Charles Parsons is credited with the invention of the steam turbine. He first developed a turbo generator in 1884. This made way for the development of the steam turbine. With the induction of the turbine, the speed available was high, necessitating changes in the reduction gear arrangement. The advantages of steam turbine over reciprocating steam engines were generation of tremendous amount of power with fewer parts, high power to weight ratio, and exceptional efficiency. The first steam turbine was installed on board SS Tubinia. This radial flow turbine rotated at 2000 rpm. After several trials and improvements, she clocked 35 knots. The propulsion system of the ship consisted of water tube boiler, radial flow turbine, and screw propeller. The Titanic, a true engineering marvel of its time, was equipped with 3 main engines, 2 reciprocating 4-cylinder steam engines, and 1 centrally placed low-pressure Parsons turbine, each driving a propeller. The 2 reciprocating engines had a combined output of 30,000 horsepower, and the output of the steam turbine was 16,000 horsepower. Combining reciprocating engines with the turbine, fuel usage was reduced and power output increased while using the same amount of steam. Steam engines were utilized on board warships as well. The Demologos, built in 1812, was the first warship to be propelled by a steam engine. She was designed by American shipbuilder Robert Fulton and was powered by 1 steam engine along with 2 paddle wheels. Construction of the Demologos paved way for shipbuilders across the globe to develop warships propelled by steam power. Steam propulsion gave warships additional speed, mobility, and maneuverability, thus enhancing the strategic power of maritime forces. Mighty warships, which fought in both world wars, were the greatest example of efficient use of steam-powered engine. Steam propulsion systems have evolved over the course of time and are even today in use by world navies. The Indian Navy too had operated a number of steamships, including aircraft carriers Vikrant and Virat. This technology is still used on many frontline warships, including the aircraft carrier Vikramaditya. The history of marine propulsion has been a testament to the unlimited perseverance and innate inquisitiveness of humankind. This journey of discovery is filled with as much technological growth by the scientific community as the sense of adventure and sacrifice by the seafarer. The growth of marine propulsion has been nothing short of a technological revolution and has been an integral part in the saga of human evolution. With this, I complete my presentation, sir. Now the house is open for discussion. Thank you, sir.
Thank you, Lieutenant Solanki, for this very interesting review from so many centuries. Now, what I suggest is that there's one question from Ekam Singh Channa saying that, can you please explain the Great Britain again? But due to shortage of time, what I suggest is let us also have the presentation by Mr. Pankaj Misra, and we can take the questions together. So request all participants to please put your questions in the chat box. And now maybe invite Mr. Pankaj Misra. Now he has got a very interesting presentation which talks about the merchant marine, tremendous improvements in technology over the years. And may I now invite Mr. Pankaj Misra, please.
Pankaj, you need to unmute yourself. Admiral Rao, sir, Pankaj is unmute.
Yeah.
Yes, sir.
Unmute.
Yeah. Sorry for the. I heartily greet the dignitaries present here, and thanks IMF for giving me this opportunity to present the technology evolution. I will be covering this part mostly on the. Yeah. So I will. Can someone confirm that the screen is visible on the presentation?
Yes. Yeah. Please go ahead.
Yeah. Thank you. So I will touch upon the development of engines, the history part, and then we'll touch upon the key developments on the technology front on the two-stroke engines as well as on the dual-fuel engines. Then following that, we will look into the various propulsion solution when we talk at the vessel levels, and then of course capturing the summary. So basically to introduce that, each year the shipping industry transports nearly 2 billion tons of crude oil, 1 billion tons of iron ore, and 350 tons of grain. Shipping's ability to offer economic and efficient long distance transport puts it at the center of the world economy. And we have seen that shipping has developed highly sophisticated logistic chain, delivering just-in-time parts and goods to manufacturers and end consumers. Today, the shipping industry has come a long way from using the simple logs to the modern autonomous ships. The evolutions always searched for the fastest, cost-effective way to ship their items. And the important point here is that technology played the key role and is constantly changing the industry. If we look at the drivers in the technology evolution, demand in trade required ships of larger sizes to be built so that more cargo could be transported to satisfy the demand. And then energy efficiency. In past times, the landscape was very different from the present one, wherein the development was driven from the high oil prices. Nowadays, it is more driven from the regulatory compliances. If we look at the incentives which a ship owner can enjoy by avoiding the levies on the bunker fuel, which is a carbon tax on top of the oil price. For the emission trading systems, the carbon dioxide is traded on the land-based applications, but the topic is also under consideration in the maritime industry. Then we have greenhouse gas concern charterers affiliated with the Right Ship Commercial. Poseidon Principles, this is an agreement reached between the finance sector and the shipping industry to integrate the IMO's policy on climate change into ships' finance decision. Sea Cargo Charter, then it refers to a framework for assessing and disclosing the climate alignment of ships chartering activity around the globe. I think this part has been very well covered already, so I'll just skip this. I will just touch upon the historical development on the engines. In 1905, the first reversing marine engine was developed by Sulzer. It led the way to the first valveless two-stroke engines at sea, 2559 kilowatt Sulzer 4S 6A engines in the Italian cargo ship Romagna in 1910. Then the development took place, and in 1920, the Sulzer became a famous name for diesel engines in the ships, power plants, and railways around the world. 1930s, ALS injection became standard in all engine types, greatly improving their efficiency and reducing their maintenance requirements. The next step was the development of turbocharging, greatly improving the power concentration of the engines with less weight and less space requirements. Then going forward, in 1970s, the first low-speed marine engine in the world running on gas entered in the service in 1972. The Sulzer 7 RNMD90 engine was running on natural gas in the Norwegian 29,000 meter cube LNG carrier Venetor. In 1980s, we have seen a very important milestone in technology development. This was a radical change in scavenging from loop to uniflow, which was made in 1983 with the introduction of RTA low-speed engines of 380 to 840 mm cylinder bore, increasing to 960 in 1994. In 1981, test with electronically controlled fuel injection began on a 4-cylinder research engine. Then in 1986, the Wärtsilä basically began development work on the dual fuel engines. The first concept being the gas diesel engine with high pressure gas injection. And this was followed by 1990s, wherein the world's first large electronically controlled low-speed engine with common rail injection was introduced and running on diesel, in the diesel technology at Switzerland. Then in 1991, the development of Wärtsilä spark ignited engine. Then we have seen the milestone of MARPOL Annex 6 NOx emission levels of Tier 1. Thereon, in 2000, the first RT Flex entered in the service in September 2001. The world's largest diesel engine are now the 14-cylinder RT Flex 96C engines producing up to 18,080 kilowatt. This has entered into service in September 2006. For practical purpose, I have included the timelines till 2015 for taking this presentation. Then in 2010, February 2011, the project began to develop the dual fuel engine gas technology for low speed engines as a solution for complying with the upcoming IMO Tier 3 emission levels requirement. Then moving forward later in 2011, Generation X engines were introduced in the market. These were offering greater efficiency in terms of fuel consumption and emissions, going down further low on the RPM side, and a large bore developed further to optimize on the energy efficiency part. Then in 2013, the XDF engine series were introduced. These are the dual fuel engines using gas admitted at lower pressure and ignited by a low volume of liquid pilot fuel. And this was the breakthrough in the marine industry. 2015, Wärtsilä has converted the first vessel into a methanol running powered commercial vessel. And after that, Wärtsilä W31 was launched. I will cover that part in the coming slides. 2015 also basically released blending opportunity. This opportunity was from the perspective of mixing 25% hydrogen in the natural gas, applicable on Wärtsilä SG and DF engines. I will skip the later part because 2016-17 onwards, that will probably be covered in the next sessions. So if you look at the RTX generation, the first RTX generation and the second RTX generation was having engines with every cylinder having an individual fuel pump, jerk pump, and developing pressure. And the RTX2 generation was additionally having electronically controlled exhaust fan. Then the development took place in 1998, the third generation RTX, wherein basically the Sulzer common rail development took place, and this was one step ahead. And here the supply pump was basically delivering 1,000 bars in a common rail, and the injection was through volumetric injection control unit BECS. Fourth generation engine, we have further seen the development continued on the RT flexes and further developing on further lower speeds and larger strokes. So if we look at basically the comparison between the Sulzer RTA and Sulzer RT flex, so the RTA engines was having one fuel pump per cylinder, and this was having a camshaft system for fuel as well as for the exhaust valves actuations, variable injection timing, and those were part of RC systems. And having the camshaft was having a reversing servo motor to reverse the engine. Then in RT flex, basically the fuel pump was on the supply unit, which was delivering a very high pressure to a common rail, 1,000 bar. And the injection was controlled electronically by the VEX 9520 control system, including the VIT and VICs. The common rail was beneficial to drastically reduce the emissions at part load, specifically reduced fuel consumption also at low loads, and possibility to reduce the further emissions and developed with lower minimum engine speed and a high precision on engine related system like cylinder oil consumption, etc. Then I will cover something on the gas burning technologies. There were three gas burning technologies: auto engines operating on low pressure gas, and they meet the IMO Tier 3 NOx requirement. Gas is mixed here with the intake air and compressed in the cylinder. Combustion is initiated with a small pilot fuel injection. This diesel pilot fuel rapidly undergoes pre-flame reactions and ignites due to heat of the compression, just as it would do in a diesel engine. The combustion of the diesel pilot then ignites the air fuel mixture in the rest of the cylinder. Then the second one is spark ignited, or the SG engines. these are the Otto engines, and their emissions are similar to the DF engines. The drawback here was that there was no fuel redundancy. There was no fuel flexibility here. And the third one is gas diesel, or the gas diesel engines, these cycle, meaning that the combustion air is compressed and the gas injected under high pressure into the combustion chamber, just like diesel engines. Of course, the Otto engines have the lower combustion temperature peaks, and thereby producing less NOx and complying with the IMO Tier 3 requirements. This makes the Otto cycle quite interesting. So now on the dual fuel engines, since the air and the primary fuel are pre-mixed in the cylinder, dual fuel engines have many features in common with the spark ignition Otto cycle engines, because they rely on the compression ignition of the diesel pilot. However, they also share some characteristics with diesel, as well as some unique advantages. Now, if we look at the advantages, it gives the fuel flexibility. It can run on multiple fuels. This engine can run on multiple fuels, and including starting, stopping, maneuvering in gas mode. This is one of the very, very crucial features. Full gas, full power in the gas mode with LNG quality index down to methane number 65. Of course, application flexibility and low exhaust gas emissions. And then this was a low gas feed pressure engine. The point here is to note is that these diesel engines, since they run both on the Otto cycle as well as on the diesel cycle, they give enormous fuel flexibility. In the diesel cycle, these engines looking forward can be converted to biodiesel, ammonia, methanol, and in the Otto cycle, these can be later on flexible with bio-LNG, synthetic LNG, and ammonia. The point here is basically what I'm trying to highlight is that this gives a substantial fuel flexibility and a transition technology to the future fuels. So this was on the dual fuel engine part. Then Wärtsilä 31, which was released in 2015. This represents a new generation of medium speed engines designed to set a new benchmark in efficiency and overall emissions performance. This is having the best fuel economy of any engines in its class. At the same time, it maintains the outstanding performance across the complete operating range. Through higher power output per cylinder, it enables a smaller footprint and cost-efficient installation. Wärtsilä 31 is significantly also increasing the vessel availability through longer time between the overhauls, extended up to 32,000 time between overhauls. So the technology here involved is basically two-stage turbocharging, common rail fuel injection, variable well timing, and unmatched automation system. The engine has won many awards, including the Guinness Book of, it is registered in the Guinness Book of World Record for the best energy efficient engine, giving the best fuel consumption. Though we have spoken about something on the engine side, now as the second pointer in the driver, which was on the energy efficiency side. The energy efficiency side, basically the outlook become broader in the past, and wherein they started looking, the owners, the operators, the designer, and the industry operated beyond the machinery efficiency optimization. And it went to level of shifts energy efficiency optimization, and then went to voyage energy efficiency optimization, where we talk about clever routing, just-in-time arrival, and then at a level of fleet energy efficiency optimization. So that's basically talking about the mission profile of the job and mission profile of the fleet and optimal fleet capacity usage. So when we look at the operational profile, how the system develops in the past, that we looked at earlier in design, speed, and draft, and then looked at operational profile, and lately in the past, then we were also looking at potential operational profiles because regulatory compliances were foreseen in the future, And this allows the flexibility for uncertain profiles and power sources. I think this topic has already been touched in the beginning, but what I would like to cover here on EEDI was that, since this was, if we look at that, the technologies which are defined in category A, B, C, and C, and this complies basically, on the various technologies which are listed on the left-hand side. Are innovative technologies technology category A. These are the technologies hydrodynamic in nature and cannot be separated from the overall performance of the vessel, like hull optimization, superstructure optimization, propeller optimization, podded drives, contra-rotating propellers, vane wheel, ducted propeller, pre-swirl device, post-swirl device, and twin stem. So these are something which are the technologies which cannot be separated from the overall performance of the vessel. Then technologies category B. These are the technologies that reduce the propulsion power, but not generate electricities. These are air lubrication systems, wind propulsion, and in category C, we have technologies that also generates electricity when going green. These are waste heat recoveries and solar power. So we see that how the affected component of the EEDI formula on the right-hand side is influenced by different type of technologies when we are looking at, meeting further regulations and developing solutions for the on vessel levels. So coming to the Wärtsilä hybrid, these were basically started way back in 2007, wherein this hybrid technology development started, and its integration. Basically, the hybrid is integration in the combination of mechanical electrical power and other energy sources like solar, wind, and energy storage devices. This basically significantly improves the efficiency by running the machinery at optimal load and absorbing many of the load fluctuations through the various flexible power sources. The system is designed and integrated to optimize the overall operation of the vessel. So now, why hybrid marine power? Basically, the benefits of Wärtsilä, this hybrid solution is that the fuel efficiency and savings and reduced emissions, optimized engine performance, reduced engine transient loads, increased redundancy and efficient operations, reduced maintenance, and increased performance. So this was these are the basically aspects hybrid marine power is covering and offering sufficient substantial flexibility. If you look at this schematic, you can see on the technology front we have an inverter and energy management system. And this is basically this energy management system is a key element in hybrid control algorithms for load sharing between the units and efficient power and energy management system. This is the brain of the complete system, which is integrating energy from various sources. And the idea here is to map the mission profile of the vessel and backend design the system accordingly to see that how the more flexibility and more energy efficiency can be brought in overall design. This is one of the example of hybrid system for. This is a double-ended ferry operating in Norway. It's having a hybrid power system. You can also see on the right-hand side that it has got an automatic mooring and inductive charging system. So when the vessel approaches the terminal, the charging system, the inductive charging system, which is a wireless charging system, it prepares automatically on itself and charges the battery on the ships. So So from historical evolution to the future, the message here is that technology evolution will continue regardless of the fuel being used, and investing in fuel flexibility and the combustion engine will mitigate compliances and business risks which are introduced by the future fuels. Though I have been given this job only to address the past part, though I would have loved to address the future technologies, which is quite interesting. But then you can follow the same on Whatsilla.com, marine decarbonization, the story going forward. And then these are my contacts. You can get in touch with me for any further queries and questions later on. Thank you so much for listening and patience. Look forward.
Yeah. Thank you, Mr. Pankaj Misra, for such a brilliant exposition. I must really congratulate IMF and NMF for giving us this opportunity to listen to people like you, who must be, I think, bursting with ideas for the future, and had such enormous knowledge of the developments. And I think that we've all learned a lot.
Thank you so much.
There are, once again, due to shortage of time, what I'll do is I'll just record the questions so that which can be answered time permitting at the end of today's session. Dr. Rana would like to know whether this is Commodore Rana, who is formerly Indian, high-speed 4-stroke engines can also use methanol or hydrogen. This is one question. There's one question from Mr. Sudarshan Pawar saying, how do you address methane slip in DF and LNG engines because if you have dual fuel?
Yeah.
So these are questions which will which you can be able, which I think I hope the organizers will allow us to listen to the answers. But since we are going into session 2, we will leave the answers till later. I just thought there's also one question addressed to me, but I believe it should be the keynote speaker. When he talked about autonomous vessels, there is a question from Mr. Muhammad, who says, what about piracy? When you have autonomous vessels, can pirates take over the autonomous vessels, and how will we protect them? So you'll you won't have ship operators, but you'll have marine commandos on the autonomous ship. So this is another question. Now, once again, I'll leave it to Admiral Nadkarni to provide time for answers. But I feel now, in all fairness to session 2, which is also very interesting, may I now hand over to Admiral Nadkarni to please launch 2.
Thank you, sir. So we will probably keep these questions till later, because I think we are little overshot the time, as Admiral Rao has also mentioned. So we'll do the honors as far as the presentation is concerned, and just firstly spotlight everyone. And now may I request Kabro Chitnis to do the honors and present a memento to the moderator and the speakers for session 1.
Thank you. On behalf of the National Maritime Foundation and the Indian Maritime Foundation, it is an honor, sir, to present you a memento, Admiral Rao, sir. It's been so great to see you after a long time. And I wonder if I recall when I first met you when you were Commander E of Vikram. Who won't remember that? Anyway, here's the memento for you, sir. Thank you very much for moderating the session. And it was very nice indeed. You were a little short of time, but we will get you back again, sir, for your comments. Thanks a lot. And may I like to present a memento on behalf of the NMF and the IMF to our first speaker of the day, Lieutenant Commander R.P. Solanki. Thank you very much, Lieutenant Commander Solanki, for a very nice run through history indeed. And we it is flow. I mean, everyone has it in the back of mind but when you present it together like this, it becomes all the more interesting. Thank you very much for your time, and thank you for the presentation. And finally, Mr. Misra, it has been enlightenment for me, actually, personally, because well, I've not delved so much in marine engines as I've dwelt in aero engines, and the use of marine engines from the bridge has been my forte rather than being down in the engine room. But this has been a great pleasure listening to indeed, and a great enlightenment. Thank you. On behalf of the IMF and the NMF, a memento for you. And I hope you got the memento. You got the memento in time. Yes. Thanks a lot indeed. Just
thank you so much, sir.
You can't see it. Yes.
Thank you so much, sir. Thank you so much for this. I love this, and I will cherish this memento for my lifetime.
Thank you very much indeed. Thank you for sparing your time being with us. And it's back to Admiral Nadkarni for the continuing the proceedings.
Thank you, sir. Just
thank you all of you, this first session speakers, and Admiral Rao, the moderator.